Vanakkam, apa kabar, ni hao, everyone. I am Logan and my teammates is Kiew and ZHEN. Today we will be presenting the key aspects of our piping system design for a process cooling system. Our focus will be on a pipe diameter calculation, material selection, pump specification, and the integration of theoretical calculations with simulations to ensure optimal system performance. Firstly, explain the basic concept of piping system and pumps. To calculate the pipe diameter, we use the continuity equation, balancing velocity and system capacity. We set a velocity limit of 3 meter per second and a flow rate of 5 meter cube minute, resulting in a diameter of approximately 0.188 meters for efficient flow. List and describe factors affecting centrifugal pump output and efficiency. So, we choose stainless steel for its corrosion resistance and durability, ensuring long-term reliability and minimizing maintenance. And for the factors affecting centrifugal pump is, for the pump, we selected centrifugal pump due to its efficiency and reliability, calculating power requirement of 24.879 kilowatts to optimize energy use. Our theoretical calculation provided a solid start, while simulations fine-tune the design for efficient operation. Consider result from both methods confirm our design's validity. As I was talking about the third one, design a complete piping system and the principles, which is this. And the last one, overall our design process including material selection and simulation has created a durable and efficient piping system. Next, I'm going to proceed to theory and concept of piping design and pump selections. Key considerations, which is flow rate, velocity, pressure drop, and head requirements. Pipe sizing, calculate pipe diameter using the continuity equation. Pump selection, determine pump head to overcome elevation differences and pressure losses. And calculate the hydraulic on flow rate and head losses for efficiency. And next part is methodology. Calculate suitable pipe diameter to ensure velocity is less than 3 meter per second. Determine total heat required by the pump. Calculate pump power and simulate system using pipe flow expert to calculate the pump calculations, the piping calculations, and the heat losses, minor losses, and the frictional heat losses.
Hi, my name is Q. Now I will explain about the pipe diameter calculation. First, the given flow rate is 5 meter cube per minute, which is equivalent to 0.0833 meter cube per second. Then, the maximum allowable velocity is 3 meter per second. By using the continuity equation, Q equal to AV, we can calculate the area A. Thus, the result will be 27.7661 times 10 to the power of negative 3. Therefore, we can use the formula of A equal to pi d squared over 4. We can get the diameter of 0.188 meter. By using Reynolds number formula, we can calculate the pump head. Re equal to rho Vd over mu. We can get a value of 706.77 times 10 to the power of 3. Thus, the value is greater than 4000. The flow will be turbulent. Next, we can calculate the Darcy friction factor, which is F equal to 64 over Re. The value will be 90.55 times 10 to the power of negative 6. Next, we have to calculate the head loss, which is equivalent to K will be coefficient, V will be velocity, and G will be gravitational force. Thus, we can get the value at elbow 90 and head loss at gate valve. Next, we also have to calculate the head loss at condenser exit and head loss at condenser entrance. Then, we can calculate the head loss minor, which is equal to 5 head loss at elbow 90 plus 3 head loss at gate valve plus 2 head loss at condenser exit plus 2 head loss at condenser entrance. Then the value we get is 3.454 meter. Last, we have to calculate the head loss measure, which is equal to F LV square over 2 dg. The F will be Darcy friction factor, L will be length of the pipe, V will be velocity, D will be diameter of the pipe, G will be gravitational force. Then the value we get is 8.217 times 10 to the power of negative 3 meter. Finally, we have to calculate the head loss total, which is equal to head loss minor plus head loss major plus delta P. The result we get is 9.462 meter. Then the head loss pump equal to Z2 minus Z1 plus head loss total, the last answer will be 24.46 meter. The last theoretical calculation will be pump power, which is P equal to rho GQH over N. The rho will be fluid density, G is gravitational constant, Q is the flow rate, H is the total head, N is the pump efficiency. Last, the value we get is 24.879 kilowatt. After the theoretical calculation, we can get a result of what material of pipe should we use, which is stainless steel Schedule 10S. The reason we use stainless steel is it has a good corrosion resistance, especially in wet and humid environment, making it ideal for cooling system. Next, it has excellent durability, high strength and toughness, ensuring the long-term reliability and resistant to mechanical stresses. Thirdly, it has a smooth interior surface. It definitely will reduce the frictional loss and minimizing scaling. Last but not least, it has a good temperature and pressure capability. It's suitable for a wide range of temperature and pressure typically encountered in cooling system.
Hello, my name is Sun, and right now I'm going to explain about simulation part. And okay, what software I use in for my simulation parts? The software that I use is Pipe Flow Expert. Okay, then finally you will come out result like this. There is a circuit, and I use 8 pipe and 2 pump and 12 pipes fitting, and the circuit is like this, and water come out from the condenser and go through a 90-degree, then and this pump act like a control valve, then go like here, then 90-degree again, then 90-degree again, and go to the spray, then it's an end pressure point. Then this is a basin, and it will come out with a condenser exit, then 90-degree again, and here also 90-degree, then come out, and here is the main pump we're going through, and is a gate valve. This one is a control valve, then going back to the condenser again. And that is a simulation circuit that I did in the software lah. Okay, this one is a simulation part for the pipe result. Then as you can see, then every material is stainless steel pipe, which can avoid the eruption, and the inner diameter that every pipe I use is 188 millimeter. Length is different based on different situation. Okay, there's a mass flow, volume flow, which is maintained at 0.0833, which is the question given require, and the velocity also 3 meter per second. And this one is friction loss, control valve loss, pump head. Okay, and this one is a pump result, and for the P2 is like a control valve, so it's not important. For the P7 is most important that we use is can get the RPM, then velocity, flow in, flow out, then suction pressure, and important is a pump head loss, pump, and the pump efficiency. This is a result that I get, which can be used to compare our theoretical calculation. Pump power kilowatt 25, and this one is a result for simulation for my pipe fitting, which can use to determine our coefficient for every fitting position. So for the pipe entry shaft is 0.5, and the 90-degree bend is coefficient is 0.84, gate valve is 0.11, and the open pipe exit is 1, coefficient is 1, and pipe exit to container is also 1. Okay, this all value will use for further calculation. And okay, this one is a pump specification that I use 1350 rpm, diameter 188 millimeter, and here will show the value of flow meter cube per second, and the head loss, efficiency, and power kilowatt. And this is a graph for the pump.
Okay, now let's talk about a discussion. First, pipe diameter calculation. The pipe diameter calculation was crucial to ensure optimal flow characteristic within the system. We use the continuity equation to maintain a balance between velocity constraints and the system capacity by setting a velocity limit of 3 meter per second, and required flow rate of 5 cubic meters per minute. We calculate a pipe diameter approximately 0.188 meters. This careful consideration ensures efficient flow performance while adhering the practical constraints. The next part is the choice of pipe material played a significant role in our design. We selected stainless steel due to its superior corrosion resistance and durability and longevity, making it ideal for the demanding operating conditions of the process cooling system. The corrosive process cooling system, the nature of the fluid, and the requirement for long reliability were key factors in for stainless steel over other materials. And we go to the pump specification. The specification of pump was another critical aspect. We choose a centrifugal pump for its efficiency, reliability, and ability to meet the system's head and flow rate requirements. Factors such as pump speed, fluid properties, and system design were considered to ensure the optimal pump performance. Using the hydraulic power equation, we calculated the pump's power consumption, resulting in a power requirement of 24.879 kilowatts. This informed the selection of an appropriately sized pump, optimizing energy consumption and ensuring efficient operation over the system's lifespan. And the fourth part is the design process integration. The theoretical calculation provided a solid foundation for designing the piping systems. Simulations were employed to validate and fine-tune the design, ensuring the system operates efficiently with the specified parameters. While differences can arise between hand calculation and simulation results due to simplifications and assumptions in manual calculations, to the data obtained. The fifth part is efficiency and performance. So efficiency and performance, our design ensures efficient flow performance, which is a pipe diameter which is 0.188 meters. The last part, the material selection, which is the stainless steel that we selected, ensures the system's durability and reduces maintenance needs, while our design process minimizes system downtime by integrating theoretical calculation. So here we go for the conclusion. The design piping system meets the required specification with a pipe diameter approximately 0.188 meters and a pump power of 24.879 kilowatts. Simulation results corroborate theoretical calculations, confirming the system performance and reliability. This process highlights the importance of combining theoretical knowledge with simulation tools for effective piping system design.